An alternator is the heart of your vehicle's charging system, converting the engine's mechanical energy into electrical energy to power electrical components and recharge the battery. Proper wiring is crucial for its efficient operation, ensuring the battery stays charged and electrical systems function correctly. Bad wiring can lead to a dead battery, electrical fires, or damage to other components. An alternator consists of four key components that work together to generate and regulate electrical power. These include the rotor, stator, rectifier, and voltage regulator. The rotor is an electromagnet driven by the engine's crankshaft. It consists of wire coils wound around an iron core with alternating north and south poles. As it spins, it creates a rotating magnetic field that induces electricity in the stator windings. The stator is a stationary set of wire coils arranged in a ring around the rotor. As the rotor spins and its magnetic field cuts through these coils, it generates alternating current, AC electricity, through electromagnetic induction. This AC power is the raw output of the alternator. The rectifier converts the alternating current, AC, generated by the stator into direct current, DC, that the vehicle's electrical system can use. It consists of diodes arranged in a bridge configuration that allow current to flow in only one direction, smoothing out the AC waveform into steady DC power. The voltage regulator ensures the alternator produces a steady output voltage, typically between 13.5 and 14.5 volts, regardless of engine speed or electrical load. It controls the strength of the rotor's magnetic field by adjusting the current flowing through the rotor windings, preventing overcharging that could damage the battery or undercharging that could drain it. Together, these four components, the rotor, stator, rectifier, and voltage regulator, form a complete alternator system that converts mechanical energy into regulated electrical power for the vehicle. A basic alternator wiring diagram includes these key connections. First, a heavy gauge wire, typically 10 to 12 AWG, connects the alternator's output terminal directly to the battery's positive terminal. This wire is often fused for safety. Second, a smaller sense wire connects to a switched ignition source to monitor battery voltage. Third, a ground connection links the alternator case to the vehicle's chassis. Finally, an optional connection powers a dashboard warning light. Use the correct wire gauge for your application, as shown in this reference table. The alternator's main output wire connects directly to the battery, delivering the electrical charge that powers the vehicle's systems and recharges the battery. The sense wire connects to the voltage regulator and monitors the battery's voltage level. This feedback allows the regulator to adjust the alternator's output, ensuring the battery receives the correct charging voltage. The ground connection completes the electrical circuit, providing a return path for current to flow back to the alternator and battery, ensuring efficient operation of the charging system. Voltage drop across wires should be minimized to prevent undercharging. Use Ohm's law, V equals I times R, to check for excessive resistance in the circuit that could cause voltage loss. Always ensure all connections are secure and corrosion-free to maintain proper charging system performance and prevent electrical faults. Modern vehicles use smart alternators that communicate with the engine control unit via CAN bus for efficient charging. This communication enables variable output, where the alternator adjusts charging based on the vehicle's electrical load for better efficiency. In hybrid vehicles, alternators assist with regenerative braking, where the electric motor reverses to generate energy and recharge the battery during deceleration. Common wiring issues in alternator systems include loose or corroded connections, which can interrupt electrical flow. Voltage drops occur when wires are too thin or damaged, reducing charging efficiency. Faulty voltage regulators may cause overcharging or undercharging, while diode failures prevent proper AC to DC conversion. Belt slippage can also reduce alternator output by slowing the rotor. Symptoms of alternator wiring issues include a dimming battery warning light on the dashboard, indicating charging problems. A dead or frequently weak battery suggests insufficient charging. Erratic electrical behavior, like flickering lights or failing accessories, points to unstable voltage. Overcharging can cause excessive heat and battery damage. To troubleshoot, first visually inspect wiring for damage, corrosion, or loose connections. Clean any corrosion and tighten connections securely. Second, test the alternator's output voltage using a multimeter. With the engine running, measure between 13.5 to 14.5 volts at the battery terminals. Lower readings indicate charging problems. Third, perform a voltage drop test to check for resistance in wiring. Connect a multimeter across connections while the circuit is loaded. Readings over 0.2 volts indicate poor connections. Fourth, verify the voltage regulator by testing field circuit resistance or replacing it if output voltage fluctuates. Consult service manuals for specific procedures. When working on alternator wiring, always disconnect the battery's negative terminal first to prevent electrical shock or short circuits. Use the correct gauge wire, typically 10 to 12 A to G for the main output, to avoid voltage drops and ensure proper charging. Use crimp connectors and ensure they are securely fastened to prevent loose connections that could cause failures. Double-check your wiring diagram against the actual components to ensure all connections are correct. Avoid using mismatched wire gauges, as this can lead to overheating and potential fires due to increased resistance. If you're unsure about any step in the wiring process, consult a qualified mechanic to avoid safety risks and ensure proper installation. With the rise of electric vehicles, traditional alternators are becoming less common. However, they will still be present in legacy internal combustion engine vehicles and mild hybrid systems. Solid-state alternators with higher efficiency are being developed, using silicon carbide semiconductors to achieve up to 95% efficiency compared to 70 to 80% in current models. Future systems will emphasize digital integration and AI-driven load balancing for more efficient and sustainable charging, as seen in modern EV infrastructure.